I'll hand over the baton to Angela Murillo, who's the co-PI on CI Compass to run the session. The only thing I would say before I do that is that Chris Bontempi is getting the award for the best abstract for putting in Schadenfreude in it, which is usually not seen in other descriptions. So thank you, Chris. Angela?
Thanks, Eva. Thanks everyone for being here. Our next presentation is from Chris Bontempi from the Networking for Advanced Nuclear Magnetic Resonance, and his presentation titled Just FTP It. He'll be talking about some of the unexpected challenges that they had from acquisition to first storage architecture. And with that, I will hand it over to Chris. Thank you.
Awesome, thank you. Can everyone see the first slide?
Yes.
Good. Okay, so here's what I'm going to talk about, the agenda, as it were. I think it's pretty, I think you hear a lot of this, but basically brief overview. I'm going to spend most of the time on issues and lessons learned, and then talk about current and future challenges. So the project overview, NMR stands for nuclear magnetic resonance. That's the technology we're using, and the devices, the instruments, are spectrometers. The project is a network for advanced NMR. It's a NSF mid-scale. It's a joint project between UConn, the University of Georgia in Athens, and the University of Wisconsin-Madison. Right now, it encompasses about 19 spectrometers, depending on what's taken apart and put together at any given time, at these three facilities. And the project actually includes funding for the first publicly available 1.1 gigahertz class spectrometers in the US. There are others, but these are the first publicly available ones. And then our infrastructure and our operations were evaluated with Trusted CI over a 6-month workshop. Just tremendous engagement in terms of securing data, making information available, reviewing infrastructure. So I highly recommend that. The objectives of the project, the main one, the elevator pitch piece of it, is to democratize the use of NMR. So the things that we're trying to do to provide that, we're archiving the NMR data, obviously employing good data stewardship and fair principles. We want to promote the NMR facilities and the services that they provide, aside from just the instruments. We're providing extensive knowledge bases aimed at various levels of expertise, so from novice all the way up to super experts. And then we're providing management tools and a conduit to publishing results. And then one of the things we really wanted to do was be able to accommodate various fields of use. This will come back into play later on. But as an example, biology and biophysics, chemistry, material science, metabolomics. We want to obviously thank the PIs. Without their wisdom and their guidance, none of this would be possible. Jeff, Chad, Katie, and Art. And then I just want to draw your attention to the right-hand side of this slide and explain that NAN, which is at the acquire phase there, is really just a part of a whole family of products. You can do a lot of processing with a platform called NMR Box. We provide sharing capabilities with BMRB that help in the publishing aspect of things. And then we also have a sort of a game theory approach to NMR with NUSCON. So this is in the context of a family of products. A couple of early considerations for NAN data ingest. So we decided NAN is a supplement to whatever kind of backup or storage facilities or storage capabilities that a facility might have. We're not positioning this as a replacement for that. And one of the other things we realize is that we're more likely to get more data if we make this relatively simple and require as little or as few user steps as possible. The stretch goal is to have no extra steps, but I don't know if that's entirely possible. So the question came up, should we just keep it simple and have people FTP their data into the repository and then we'll work with it from there? And after some deliberation, we realized, no, we can actually provide value by automating that aspect of it. So fewer user steps and more consistency of the content. Because if folks are always FTPing their own data in. There may be things they include, things they don't include. This gives us a little more, a better shot at consistency. So talking about the data lifecycle, this is kind of the overall lifecycle. We have the pre-configured settings, things like the facilities and the spectrometers described, information about the users, where they are, what their projects are, what their samples are that they're using, those kinds of bits of information. And then we currently are looking at 3 different data acquisition modes. The first is that automatic, collected as it's generated mode. We've also provided a historical results mode that you can upload from an active spectrometer. So if, for example, you missed collecting the data or harvesting the data when it was collected, or if it predates NAN, you can actually upload it from the spectrometer itself. We're currently working on the capability of uploading archives of experiments that we'll tear apart and parse. That's soon to come, and it introduces a lot of ideas or a lot of questions about, the freshness of the data and the accuracy of it in some senses. We can kind of guarantee, not guarantee, but come close to guaranteeing almost entirely the provenance of data that we collect live as it's going on. But the other two have to sort of reside in a different class of data. So that's the acquisition. The data is received and staged in the landing zone. This is sort of a pre-area before the repository. We parse the data into the repository, assign identifiers, and the contents are interpreted. From that point, the experimenter and the PI of the experimenter, if they're not the same person, they can manage, modify, publish, share, remove experimental data, whatever types of things they want to do. The original data is always preserved. We archive it on write once, read many devices. And currently there are a little over 300,000 experiments harvested to date. This graphic down in the bottom left is representation of our data browser, which allows people to look at the experiments that they've collected, anything that's been shared with them, and anything that's public. So they can search through that, download them, do all kinds of things that you want to do with the experimental data. Drilling down into the data acquisition part of it, this picture on the right here kind of represents what that acquisition looks like. The bulk of it is over on the left-hand side of that picture. But we need to detect and determine the configuration, the settings, who's collecting this data, what device is it being collected from, that sort of thing. And then we have to be able to detect an acquisition start and finish, so the spectrometer actually doing its bit of work. You can see that we have these spectrometers, and they're always going through a gateway before they come into the repository area. That's because the spectrometers run on a lot of different operating systems at a lot of different versions, some of which don't support modern cryptography. We have a couple that run CentOS 5, for example. And some devices and some spectrometer workstations aren't even really allowed to talk to the outside world. They're completely contained within the network at the facility. So to get around these limitations and to kind of create one common way of doing things, everything goes through a gateway, which is really just a Linux computer that has modern cryptography. It provides secure and reliable transmission. So the steps are that the agent on the spectrometer workstation detects an acquisition complete. It will take the data and copy it to the gateway. If the information is not, or if the gateway is not available for some reason, it just copies it off to a different space on the spectrometer workstation, and then it will keep retrying until the gateway becomes available. Same sort of action for the gateway. The gateway receives the data and it tries to send it to the receiver at the repository. If it can't, it will buffer that data there for, I think we have, probably something like a week or more leeway there. Hopefully we don't have a situation where this stuff is down for more than a week. I think we have bigger problems if that's the situation. The data arrives, it triggers a parser operation. The parser takes the data, moves it into primary storage, adds entries to the NAN database, writes visibility statistics to Elasticsearch, and then the experiment is now available for the users to manage. All right, So that was the overview of kind of what it is and what it does. Here were some of the challenges that we ran into. I'm going to go through these here. All right, so identifying discrete units. So one of the first things that we noticed is that the experiments, nothing's really tagged with a unique identifier that comes from the system. So there's nothing system assigned there. We had to kind of come up with our own. And then because we support these various different fields, we're noticing that there are different units of interest. So kind of where we started and what was typical is you have a matched set of parameters and results on a single sample. So set up the parameters, do the acquisition, get the results, and those three things go together, the parameters, the results, and the samples. So that's kind of an individual units idea. But we also found that we had these combined units where you might have a matched set of parameters and results, but different samples. And the example of this is metabolomics. So they might have 200 samples that they'll want to do the same experiment on each one. Now, you want to think of these things together as kind of a single unit to some extent, but the results don't correspond to one another. You wouldn't compare the results necessarily. You might at some point. But that's in contrast to the next one, which is this calibrating idea, where you continuously shift the parameters slightly, and you have these results that are generated from a single sample, but you want to compare them to see what the progression of the results is relative to the parameters. So already we have three different ways of looking at these things. And one of the things that challenged part of this is this idea of transience. So some of the machines will insert kind of a pulse beforehand or a pulse afterward or a pulse in the middle of some other things that make it very difficult to tell exactly which piece is of the most interest. So you might see three things that are all clustered together, and the experimenter doesn't care about the first thing or the last thing. They only care about the thing in the middle. That's not even always the case. So that was another piece we had to kind of deal with. And then the user has a lot of latitude for designing exactly how these pulses are sent. So it's difficult to come up with a discernible pattern. In other words, we can't really whitelist what we wanted to do. We kind of had to blacklist what we want to ignore. And that blacklist is really, really short. It's very small because we're finding we can't, it's perilous to try to think that we can ignore certain things based on things like time, the duration of the experiment, those types of things. But it did raise the question for us in terms of what we're identifying. So we have these acquisitions, and there's all these different multi-part acquisitions. How do we look at them? How do we figure out what kind of thing we're looking at? We also have this question about the upload attempts. So if we have something that we've identified as a single unit or whatever, and we try to upload it, and it fails, maybe the network drops or something along those lines, and then we upload again. Now we have the same experiment that maybe is represented in the database or represented at least at the receiver twice. And how do we differentiate between those? And how do we resolve potential differences between those? Because maybe the first attempt copied, 90% of the files, and the second attempt copied 100% of the files. Do we really know that difference is a reasonable one? And how do we tear the pieces apart to figure that out? The main question that it raised is what is the real thing? And we're finding that the real thing that we're looking for depends a little bit on the circumstances, who's doing it and what exactly they're trying to accomplish. So that was a set of early issues. And this was another set of early issues, the workflow considerations. So we wanted to be able to allow the users to opt out if they want to. If they don't want to collect their data, then we want them to be able to tell us that. We also want the facility manager to be able to say, hey, if this person logs in, we don't want them to collect their data. They're not supposed to do that. Or we want that turned off by default and then allow the user to turn it on. So we have both of those modes of doing things. We also wanted to allow the users to be able to provide information that we can't harvest off the machine. Information like the sample that they're using, which there's nothing really that tells us within the context of these machines what the sample is, the project that the user's working on, the funding, that type of thing, which obviously is not going to be on the spectrometer. And then the actual user that's running this experiment or the person it's supposed to belong to, because the user directory between the spectrometer and NAN is never going to be the same thing. They're not ever going to be the same detailed stuff. So we have to figure out who's actually running the experiment. This is because a lot of people can be logged into the workstation at the same time. A lot of people can actually be running the spectrometer control software at the same time. Only one user is actually controlling the spectrometer. So we have to be able to figure out who that person is. And thankfully, there's a way for us to do that relatively easily. But we also have to be able to detect when that changes. When does it change from one user to the other? Be able to do that accurately and be able to keep those settings separate so that we don't assign an experiment to somebody who happened to have been running the spectrometer 5 seconds ago and now they're not anymore. So that was a bit of a challenge. Another challenge was reliable transmit and receive. I think the folks before me kind of alluded to an idea like this, but there's automation software on the spectrometers that allows them to do acquisitions in very rapid sequence. Sometimes the data gets overwritten, the results get overwritten before we can actually collect the information. And what do we do when that happens? Identifying what's missing, identify what might be broken, and being able to have the system handle pieces that might be missing to present to the user, hey, here was something you tried to go and get. We did the best we could. Here's what we got. And then, of course, we want to make sure that none of it's damaged by transit and that sort of thing. Secure transmission, obviously, we don't want to have any snooping. Good citizen behavior. We don't want to cause any problems on the network. We don't want to create any vectors for attack. Never interfere with the device and the storage. We want to be able to detect when there's downtime of the NAN system so that someone can, if they need to manually intervene, they can. But at the same time, we want to limit the amount of manual intervention that's required. So automatic retries when things get back to normal, if they get back to normal on their own. And then, as I mentioned before, trying to detect these true duplicates in the landing zone, stuff that comes in, hey, we've already seen this thing in particular. But because we don't have unique identifiers, we can't use that as something that would help us do that. We have to use the clues that are actually embedded in the data themselves. These things I would refer to as kind of single points of failure or points of failure that might require hardening or more focus over the years. As I mentioned, we have a lot of variation in operating systems and the standards supported. So we have to pay a lot of attention to that. Every now and then we recover something or uncover something new that an old platform won't do, that new platforms do. So that's a challenge at times. We have these different pieces, the receiver, the gateway, the workstation. Obviously, failures in any of the networks involved are going to require sort of automatic healing. There's the repository file systems, which might introduce latency at times or might go read-only if there's some kind of an issue. We have to be able to handle those kinds of circumstances. Databases, we don't see a lot of failures with them, but they do have maintenance windows, and some of those maintenance windows can be hours at a time. So what do we do while that's going on? These are all things we've had to address so far. Program bugs. We had an interesting problem with rsync. The default action for rsync is that it interprets file names before it sends the information across the network. There's a flag to tell it not to do that, and we had to enable that flag because we had some file names that, if they were interpreted on the sending side, would cause problems. So that was another thing that we found and had to kind of just fix. Then parsing challenges, again, we talked about missing stuff. If there's extra stuff, is that going to cause a problem? Somebody suggested a hypothetical. What if I decided to store my copy of E.T. the movie in my experiment directory for some bizarre reason? What could we do about something that large trying to be uploaded? Because our data sets are not very big. And what's the limit that we set it to? We've seen some unexpected character sets. We've seen files come through as Latin 1, for example, and some of the standard file readers will not be happy with that if that happens. We've seen files with XML and JSON extensions that actually violate the standards or actually cause the standard libraries to choke for whatever reason. So we've had to do sort of pre-parsing on some of those things. Recovery challenges. Something goes down for a little while, everything comes back up. We get this massive surge of experiments, for example, coming in all of a sudden. The infrastructure is designed to handle the load and then a little bit more. But if you have these massive surges for whatever reason, how do you allow the system to catch up? That's been challenging. User expectations around visibility. We're providing visibility into the system so you can see how everything's functioning. But that requires us to then be able to handle when someone says, "Hey, I see this thing is not working right. When's that going to be ready, or when's that going to be working?" We're, as I mentioned, allowing manual transmission of data for recovery. But how do we legitimize provenance in that situation? And how does that limit what the user is going to be able to do with that data? And then anticipate conditions that might make the data unrecoverable. And here again, I refer back to the facility backups. If we can get them off of the facility backups, because the data may have been overwritten, then they can use the manual upload for that. Evolving transformation. This really has to do with parsing and being able to reparse. In some circumstances, new points of emphasis are added. Hey, this thing wasn't important to people before, now it is. New perspectives. There might be a new class of user that's never used the system before. Hey, here's the piece that's important to them. We've seen a lot of that as we've added different kinds of users. If we refine calculations, hey, in this circumstance, this particular thing needs to be calculated slightly differently, but we didn't know that at the beginning. So let's go back and correct those. And then newer workstation software is being released all the time, and sometimes it's providing new information that it didn't provide before. So we want to be able to leverage that. These are all some of the reasons that we want to be able to run things back through our parser for some or all of the experiments and get richer metadata out of the data that's coming through. And then visibility. You want to obviously instrument everything that you do, every operation and process for visibility, instrument your data so that if somebody changed something, you want to be able to go back and say, here's what it was before, here's what they changed it to. And, are we sure that that's good? Understand what you have and what you missed. That's very important. And then this idea of what might be considered useless. And I've got a couple of examples here. But the upshot to me is that you may think something is useless currently, and you may choose to ignore it or leave it by the wayside. I think that's a problematic approach in some ways, because unimportant things do have a tendency once in a while to become important down the road. And if you don't collect it, you won't have it. Current and future challenges. Unexpected experiment volumes. That's one thing that we're working on. We want to be able to see that and be aware of it. But automating responses to that, I think, is a little problematic. Things like throttling. We want to make sure that we know and choose the idea of throttling explicitly. Those complex experiment groupings. How can we safely demote the things that we think people are not going to be interested in? Not remove them, just demote them. We are planning to scale up to more facilities, and I think we're well positioned to do that. So we should be adding some facilities in the next year or so. Expanding to multiple repositories. So, for example, we have to have data separation between Europe and North America. We want to have localized visibility so that, at another repository, you can see everything that's going on at that repository. I think at some point we're going to have consolidated visibility across the repositories. And then just continue to root out single points of failure, any place that might challenge what we're trying to do there. So that is what I had. Sorry I didn't leave as much time for questions, but happy to answer anything.
Thanks so much, Chris.